Welcome back to Sharp Shorts. In the second of our video series on how to name ionic compounds, today we're going to talk about polyatomic compounds. Here is a good example here, calcium carbonate, the key component in many of these seashells you see here in the picture. What you can see by a polyatomic or ternary compound is you have more than two elements. You have three or more possible elements, which, if you think back to our binary ionic compounds, they were fairly easy to name. I just named the cation, and I named the anion, and I just changed the anion ending to IDE. The difference here is where's my cation and where's my anion? And we'll talk about that, but one of the things to note, and I'll draw a line here, is if you look at a list of polyatomic ions, which we'll talk about in a minute, and you have plenty on your periodic table cheat sheet in a table of their own. The vast majority of polyatomic ions are anions, as with the carbonate anion here. There's only a couple of exceptions that where the polyatomic is a cation. The most notable one is ammonium, and we'll talk about that when it happens, but that will help you understand then that I can split this into my cation anion, because it is an ionic compound, generally by making the split right after the first element. Okay, so what are these polyatomic ions and polyatomic compounds? Well, the compounds themselves have three or more elements. The ion, the anion part, is generally, in the case of this nitrate here that I'm showing, is a group of elements, often with oxygen. Oftentimes they are a couple of nonmetals, but they are covalently bonded. So all these bonds right here are where they are sharing. Here's a double bond, here's a bond here. They are sharing their electrons to fill their octet shell. In doing that, though, often like here with the nitrate, they still might need to find another electron to fill their valence shells all the way around so that each of them has a filled octet. And if you were to count around here, 2, 4, 6, 8 for the nitrogen, 2, 4, 6, 8 for that oxygen, 2, 4, 6, 8 for that one, 2, 4, 6, there was 7. I picked up this green one, an extra one. That gave me 8. All of those elements then, the nitrogen and the 3 oxygens, now have a stable octet by sharing electrons, not by transfer as we saw in our last video, but by sharing. And then often picking up an extra to fill the valence shell. This extra electron then gives it a negative charge and allows this whole group to act as an anion, or in the case of ammonium as a cation. What separates them from binary, which have an IDE ending, is, with very few exceptions, the endings to these compounds are ATE or ITE. The two notable exceptions are cyanide and hydroxide, and you can see their structures on your cheat sheet in your polyatomic. I also want to point out for this that the use of parentheses is going to be vitally important in writing the formulas and stuff for polyatomic ternary compounds. All right. So again, as we did in our last video, the best thing is just by doing examples. All right, here's a few that we have already written in formulas. Okay. Now, in many respects, once I recognize that this is a ternary compound, or as we call it, polyatomic, and I can see that for all of these they have more than two, is that the naming is almost easier because you don't have to change any endings for the most part. Okay, unless you're working with ammonium, which we can discuss. So again, what I'm going to do is I'm going to look and really make my break between my cation and anion at the first element. And that way I know, since these are still written cation anion, where my positive charge, where my negative charge is. Now, here's my one notable exception. That is the ammonium polyatomic. For our purposes, it is essentially the only positive cation that we work with. So that would be the recognition that, oh, this is ammonium, so that is where the break occurs, and then the rest of this is negative. Now, I have another polyatomic following that, which is more than possible. I could also have just a single element following this. For example, I could just have chlorine with the ammonium, in which case then I do have to change the ending to IDE, but we won't worry about that right now. So, then it goes back to normal naming. Name the cation. This happens to be calcium. And then I go to a chart, my cheat sheet, my periodic table, and I look and see what NO3 is. And when I look, that's nitrate. That's the one we used as our example. And that's all I write. I write the anion name. Just as it's written, I don't have to change anything. The ATE ending denotes that it is a ternary compound. Okay. And again, we'll talk about these subscripts when we take the words and change them to formulas, but again, these are ionic compounds, so they have to remain neutral, so I have to balance the charges. Alright, on the next one, I've already noted that that's my one cation polyatomic, that's ammonium. Then I go back to my table, pardon my writing there, and I look up PO4, and that is something called phosphate. And now I've named it. Pardon my pen use. Last one here, my cation is lithium. And I go to my chart and I look up NO2, and that is actually nitrite. So you can see, if you look at your list, you can see that one of the features that helps you understand whether this is a ternary compound or binary or covalent or an acid base or whatever, oops, pardon my spelling, that's nitrite, is the AT or IT ending. You just have to know the exceptions, which are the cyanide and hydroxide. Now in reverse, it is just as I was doing before with the binary compounds. Just find the symbols. The one thing I will know is that I will find AT and IT endings in my polyatomic chart. I should not be looking at the periodic table for those. Cations, of course, are all on the periodic table. Lithium has a formula Li, and it's written first, so I know that's going to be positive. I'll figure out its charge in a second. Carbonate with the AT ending, I go to my chart, and that is CO3, and the chart tells me it has a -2 charge. I go to the periodic table. Lithium has 1 valence electron, so it's going to be a +1. And so the correct formula then, as I neutralize this compound, is I need 2 lithiums bound to the carbonate. Okay. Here I have calcium nitrate. Calcium is Ca. I go to the periodic table. It's positive because it's the first one written. It has 2 valence electrons, so it's going to be a +2. Nitrate, by looking on my cheat sheet, is NO3. That has a -1 charge according to the table. And this is where the parentheses come important. If I need more than one polyatomic ion, then I have to put it in parentheses to denote that I'm using multiples of those. I cannot do any crazy kind of mathematics with the 2 subscripts. That is the proper showing. Right there, calcium nitrate, showing I have 2 of those nitrate groups bound to a calcium. Okay. Same again here. Strontium is listed first, so it's my cation, and it also has a positive 2 charge by its valence electrons. Hydroxide is one of my rare IDE endings, and that's just OH. We'll see later that that helps denote a base. And by the chart, that is a -1. This is the one where it is probably most important that you do not forget the parentheses. I need 2 hydroxides for every strontium to make the compound neutral, and I have to use the parentheses. If I do not, we'll see what it looks like. There's the proper format. The wrong way to do it, which most kids will do, is they will get it together right. They will forget the parentheses, and they will just write the 2. The problem is, this denotes that I have 2 of these hydroxide polyatomics. This notes that I have 2 hydrogens only. Improper. Please don't do that. And then the last one is aluminum acetate. Aluminum is Al. It's a cation. It's got 3 valence electrons. Acetate is a complex little polyatomic with 2 carbon, 3 hydrogen, and 2 oxygen. It's got a -1 charge. So, again, it's a moment when I need parentheses to note that I'm going to have 3 of these acetate compounds to correctly write the formula. Okay? So, there you go. Ternary or polyatomic ionic compounds. They have 3 or more elements. Almost all the time, the first element is the cation, the rest of it is the anion, except in the case of ammonium. Okay. I don't have to change any endings on writing the formula, unless, for example, with ammonium, I would have just a monatomic single element there, monatomic ion. When I am writing the formulas, if I need more than 1 polyatomic, I have to wrap it in parentheses. Okay? Go take the quiz. Our next discussion will be those crazy transition metals that can have more than 1 possible charge.